All right. Good morning, everybody. Well, let's get started. I want to try to get done with this chapter today. We got a little bit left, and I'm sorry. Let me go ahead and watch. Remind me to get started with the timing. Okay. I want to try to get. We need to get done with the chapter today. I want to go ahead and finish up with the naming. So we'll get done with section 9.2 today, and then what I like to do then is there's cover the last section of chapter 7 that deals with metallic bonding, and also quickly go through the discussion of the properties of ionic compounds, and then try to wrap up this chapter today. Okay. All right. So let's go ahead then, and let me go ahead and let me share with you my screen here, and let's see here. There. All right. So what I'd like to do then is let's take a look at. We left off yesterday talking about how with the non-binary compounds. Let me go ahead and do this here. The non-binary compounds. What we should observe with non-binary compounds is that we have more than one element that makes up that particular compound. Okay, and so when you take a look at the formula for a compound, you should be able to identify that it is non-binary just from just from counting the number of elements that are present, counting the symbols, counting the number of different symbols that are there. So we finished up with this problem yesterday, and if you take a look at each one of these compounds, you will notice then that with each one of these compounds, there are more than two elements. And as a result, then all of these compounds here are non-binary compounds. Remember, binary compounds are compounds that are made up of only two elements. Okay, and so we should expect then only to see two symbols in the formula for that particular compound. So for all these compounds here, these are non-binary compounds. And what you're going to notice then is with non-binary compounds, if they are ionic, okay, if they are ionic nature, and these are, okay, you're going to notice then that they all will be comprised of at least of a metal atom. Okay, so they all will be comprised of at least one metal atom. Okay, and with that said, then that metal atom then will be your cation. So when you take a look at these compounds here, you should first of all recognize that they're non-binary. And secondly, you should recognize then that they are ionic in nature because you have a metal portion. And if you notice in the metals in each one of these compounds here will be the cation. And then the non-metal portion is the polyatomic ions. Okay? So if you take a look at these, you got to make sure you keep in mind then that the non-binary compounds, almost all of them, will have polyatomic anions. Okay? With the one exception, and please make sure you remember what that one exception is. Okay? But besides that one exception, okay, all of the non-binary compounds will have a single metal cation and a polyatomic anion portion. Okay. All right. So given these here, you should be able to name these compounds. And again, like I said, naming these compounds essentially comes down to you memorizing the polyatomic ions. Okay. All right. So we have to move on. And what we have to be able to do now is that if you are given the name of the compound of a non-binary compound, can you come up with the formula? And like I had mentioned in yesterday's lesson, you have to be mindful that it's trying to get these formulas here from the name that is a little bit more important for what we will be doing in the future, in the near future, than writing down the name of the compound. Okay, so yes, you need to know if you're given the formula of a non-binary compound, you should be able to write out its name. You have to be able to do that. But of more important, what's going to be more important for us is then if you are given the name of the compound, if a compound is described for you using its name, can you write out the formula? And that's what we have to be able to do here. Okay. And so what we're going to do here is we're going to practice, and then you're going to see then that writing out the formula for the non-binary compounds, very similar to what we did with the binary compounds. The only difference then again, you have to treat the polyatomic ion as one unit. You want to pretend that it is a single entity, like the monatomic ions were a single entity. You want to make sure then that you treat the polyatomic ions also as a single entity, a single unit, and we'll talk about that. Okay? All right, so the polyatomic ion so the rules are going to be the same. Okay? What you want to do then, you want to write down the symbols for the cations and the anions, and remember, with these polyatomic ions, the symbols will be made up of more than one element because these are polyatomic. Okay, more than one atom. Okay, so you got to make sure you write that down. Okay, then what do? You need to make sure you balance out the charges, making sure then, and this is key here, and this is what I want to point out to you again, making sure then that you remember and treat the polyatomic ion as if it were one unit. Okay? Pretend that it's a monatomic ion. Okay? Treat it as a single atom. Okay? Treat it, what you want to do is treat it as a single atom. That's what it means by single unit. Okay, but you want to treat it as a single atom. Okay, and then what you want to do then is balance out the charges either by just looking at it and making that quick calculation, or using that simple crisscross method that I taught you back when we did the binary compound. Okay. All right. The key though here, folks, the key here though is making sure that you treat the polyatomic ions as a single unit. Okay. All right, so I'm going to go ahead then and I'm going to save that so that you can be reminded of that. And let's go ahead then, let's take a look at some examples here of problems that will ask you to write out the formulas. Okay, so let's take a look at the first one here. Okay. All right, so first of all, what you need to notice, and it's going to be a bit more difficult to identify this, but you have to make sure that you can identify this as being a non-binary compound. So answering the first question from the name, from the looking what we did yesterday, writing out the formula, given the formula, you can easily see that it's a binary, non-binary compound. Okay? Given the name, it's not as easy to see. What you have to do then is, again, it comes down to you memorizing the polyatomic ions. Okay, and so if you had memorized it, you would see then that sulfate is the name of a polyatomic ion. So if this is a compound with the polyatomic ion, it definitely cannot be a binary compound. Okay, so that's what you have to make sure you do with the formula. When you're given the formula for a non-binary compound, it is very easy to see that it is not a binary compound. You can look at the different symbols for the different elements here. When you're given the name, it's a bit more difficult, only because you have to memorize it. So you have to be able to memorize it. Okay. All right. So with that said, then now that we've identified that this is a non-binary compound, we want to be able to identify the cation. Okay. The cation, remember, will always be the metal portion of the name. Okay, and it will always come first. And just like what we saw with the binary compounds, when you identify that this is an ionic compound, the cation will always come first. It is the metal, and the metal is always written first. And so make sure you keep that in mind. That means then this is the non-metal portion, and that will come second. Okay, so the non-metal portion here just happens to be made up of more than one atom. Okay, with the binary compounds, remember, the non-metal portion was made up of a single atom, a single element. Okay, it's monatomic. Okay, all right. So with that said, then the cation then is going to be the potassium cation. And the symbol for the potassium cation then is going to be K plus. You got to make sure you do that. Okay. All right. So with the that taken care of, let's go ahead and let's identify the anion. Everything left here is going to be the anion, which is the sulfate anion. Okay. Sulfate, then, you have to remember this, is the SO4 with a 2 negative charge. Okay. So that unit then is made up of 5 atoms that has a 2 negative charge. And so what you want to do then is you want to treat this as a single unit. When you balance it out, you want to treat it as a single unit, and that's where I'm going to start with. Okay, so let's go ahead and let's take a look at this. Okay, so let's imagine that we have potassium, and I'm just going to call sulfate right now the X. Okay, that's your unit, the X. And you want to ask yourself then, does one potassium cation balance out this X here? Okay? And we see that no, because if we have 1 potassium and 1 sulfate, the charge is going to be then a -1. The net charge is going to be a -1. So that doesn't work. That does not work. And so therefore, what do we need? We actually need 2 of these potassiums here, 2 of these potassiums here. And once we add that to the 1, X with the 2 minus, we then get a net charge of 0. Okay. So what I'm doing right here is I'm trying to show you then that we'll substitute sulfate back in here in just a moment. But how you want to treat the sulfate unit is you want to treat sulfate here is you want to treat it as a single unit with that charge. When you go to balance it out, that's what you want to do. Right. So with that said, then when we write this out, we're going to see then that we need 2 potassiums and only 1 of that X unit. So substituting back in the sulfate here. So I'm going to call, I'm going to replace, and that's what I did. I'm going to just quickly replace sulfate with the X here. Okay, substituting it back in. This is what we have. That is the formula then for potassium sulfate. Okay. Now, I'm not going to make a habit, and I don't want you to make a habit of doing this step right here, where you're going to substitute it for 1 unit. But initially, what you want to do then is, yes, make sure you treat, if you have to do it this way, is treat the polyatomic ion as a single unit. And if it helps you to replace it with a single variable right here, a single letter, you do that. You do that. Okay. All right. So let me go ahead then and let's say save that, and let's work through another one. Let's take a look at another one. Okay. Let's take a look at sodium nitrate here. Okay. All right. So with that said, then, is this a binary compound? No, this is not going to be a binary compound. Why? Because of this here. You'd have to recognize then that that is a polyatomic ion. Okay. And so with that said, then let's go ahead and identify. So this is not a binary compound. Okay. And so let's go ahead and identify the cation. The cation, then, remember, is going to be then the part of the name that comes first. That's going to be your metal right there. So sodium is a metal. So there's your cation, which makes then nitrate, your non-metal. This is the non-metal portion. Sorry, let me go do this. The non-metal portion. It just so happens that the non-metal portion is made up of more than a single atom, okay, but that is still your non-metal. So that makes then your ionic compound. Metal and non-metal together. Okay. All right, so let's go ahead then. Name of the cation is the sodium cation. Okay. And the symbol for the sodium cation then is going to be Na+. Okay. Which means then this anion here, that is going to be your polyatomic anion. That's your nitrate anion. Okay, so that's nitrate. And again, this formula, you got to make sure you remember this for nitrate. Then you got to remember all this is NO3-. I'm going to go ahead and I'm going to do this. I'm going to continue to do this. I'm going to refer to this one as a single atom or a single entity with a -1 charge. Okay. Right, so let's go ahead and balance this out. So for right now, we're gonna make this assumption right here. We're gonna make this assumption here where nitrate is X-. Okay, so we're gonna balance out the charges. Then we're gonna balance out the charges using that. Okay, sodium is 1, and then there's your X-. If we have 1 sodium and 1 X-, okay, what you're gonna see then is we add those together, the charge becomes 0, and so therefore, we only need 1 sodium and 1 X to balance it out. Let's go ahead and substitute that X back in. Okay, so we have then NaNO3, and that is the formula for sodium nitrate. Okay. All right. So you got to make sure then that you keep that in mind when you go about doing this. Okay. All right. Let's continue on. Let's do another example here. Let's do another example, and let's keep practicing this here. Let me say that for you. Clear that out. Let's take a look at this compound here, calcium nitrate. Okay. All right, so I think we can go through this a little bit quicker, okay, because we see then that first of all, this is not a binary compound. Why? Because if you notice here, again, there's the nitrate. Nitrate is a polyatomic ion, okay? And so therefore, this is not a binary compound. The cation then is going to be the metal portion here, and there it is. There's your metal portion. It will always be listed first, okay? Or if you want to think about it, the cation is always listed first, and the anion is always listed second. You can think of it in that ways as well. So there's your metal, and here's your non-metal portion. Okay. All right. So with that said, the cation then is going to be your calcium cation. Okay. The symbol for calcium is a 2A metal, so it's going to be Ca2+. Okay, which means then that the anion then is going to be the nitrate. The nitrate anion. Okay. And the symbol for nitrate again is going to be NO3-. And I'm going to do the same thing again. I'm going to pretend that nitrate is a single entity, a single unit that we will call just arbitrarily X-. Okay. And then we're going to go ahead and we're going to balance out we're going to work out the balance equation here. Okay. So with that said, then we have then calcium with the 2+, X with a minus here. Okay. And so if you notice then, 1 calcium requires 2 of these X's here to balance it out, to get to a 0 net charge, which means then when we write this out, it's going to be CaX2. Okay. So with that said, substituting back in our nitrate, then it's going to be Ca NO3. Now understand, each one of these X units is a nitrate. So what we have to do then is we have to put a parentheses around that to indicate then that we need 2 of those units. So that's where you got to be careful with this. Okay. So again, X represents the nitrate ion. When we substitute it back in here, okay, what we're saying is we have 2 of these X units, 2 of these nitrates, and then the only way that we can indicate that is by putting the parentheses around the nitrate here. Because if you write it out this way, and you write it out as CaNO3, and you forget to put the 2 outside, that 2 now is meaningless. That 2 can be mistaken for, say, 32, that you have 1 nitrogen and 32 oxygens. And that's obviously not the case. And so when we write out these polyatomic ions, when we write out these non-binary compounds, what you need to do then is with the polyatomic ions, if you end up with more than one of them, in the previous examples, we only needed 1 to balance out the cations. If you end up with more than 1, okay, what you have to do then is you have to place the polyatomic ion in parentheses, and then go ahead and indicate how many they have with the subscript on the outside of that. Okay. All right. Now, if you notice here, what we could have done as well is we could have crossed the charges, and we did that, bringing the 2 down here and the 1 down here. Okay, we can do the exact same thing, and we have that right here, and then go ahead and substitute in the nitrate for the X. Okay. All right. So this whole step here of substituting and that hopefully you are doing mentally. I'm going to do that a couple more times for you, but at some point, hopefully at the end of this lesson, you guys, you're not doing that anymore, okay? Because you got to make sure that you really don't have time when we do this to go through all of these steps here. All of these steps here has to be done fairly quickly, okay? And it has to be done in your head without having to think through all this, okay? Right? Because you can't afford to be answering these 7 questions and doing all this as we move on. It just takes too much time. But for right now, please do this until you get to the point where you are asking yourself these questions and answering these questions almost simultaneously as you go about doing this. It's folks, it's very much like when you learned how to walk. Okay, you get up, you start slow, you take a couple steps, but at some point, as you practice, your muscles get stronger, you're off and running. Okay? The same thing here. We got to take it slow at first, okay? But then at some point, folks, you got to go. You got to take off and start running with this. Okay. All right, let's go ahead. And again, it takes practice. Okay, so let's go ahead and let's practice this. Let's take a look at number 16 in your problem set here. Let's take a look at number 16 in your problem set. I'm going to go ahead and I'm going to work through the first 2 for you, and then I'm going to ask you to do the last 2. Okay, so let me go ahead and go ahead and open up. I'm going to open up my whiteboard here because I need a little bit more room here. So I'm going to go ahead and open up my whiteboard. Please have your have your problem set in front of you, okay? And then you can follow along. Okay, because I am going to go through all these steps here with you initially, and then hopefully by the time you get yours done, you don't have to worry about it. Okay? You are not doing this with the steps. Okay, so let's go ahead then and let's take a look at the very first one, number 1 here. And we have the potassium, okay, hydrogen, okay, phosphate. So that is the name of the compound. Okay. All right. So like I said, initially what you want to do then is recognize that this is not a binary compound because of that. That's your that compound that right there should tell you that this is not a binary compound. Okay. All right, so with that said then, let's go ahead and identify cation and anion. Okay. So the cation then will always come first, and it's always going to be your metal. So here's your cation right here. So the symbol for the cation then is going to be K+. Okay. The anion then, the hydrogen phosphate, and again, you'll know this from having it memorized, okay, is HPO4 with a 2-. Okay, so it's HPO4 with a 2-, okay, and so that's what we have right there. So we have our anion and we have our cation. Let's go ahead then and let's take a look at this. I'm gonna again, what I'm gonna do is I'm going to replace this just for right now, okay, and replace it with an X. So we have X with the 2- here. So the hydrogen phosphate is a single unit right now that we are referring to as X. Okay? So to balance this out, hopefully you see then that we need 2 of the potassiums for every 1 of these units here. And so therefore that will equal to 0. Okay. And so with that said, then when we write this out, then we have K2 and 1X. Okay. And so substituting in the hydrogen phosphate again, okay, substituting it back in, we have then K2 HPO4, and that, folks, is the formula for potassium hydrogen phosphate. Again, my hope then is that you do not at some point, this portion in red here, you are doing all in your head. You don't have to you won't have to write that out. Okay. All right. Actually, I should probably extend that. It should be all of it. So at some point, you should be able to do all of this here, okay, in your head. Okay, but that's okay. We're walking. We're learning how to walk. Okay, so let's go ahead. Let's take a look at the next one. Okay. All right. So we have then strontium sulfate. Okay. Is this a binary compound? No, for one very simple reason. Sulfate is not an atom. Okay, you will not find it on the periodic table. So at that point, then you will recognize that it is a polyatomic ion. Okay, so with that said, then, and polyatomic ions, with the exception of one of them, are always going to be the anion. So therefore, strontium is going to be your cation. Okay, so the strontium is a 2A metal, so it's going to be a strontium 2 plus. Sulfate then is going to be SO4 2 minus. Okay. All right, let's go ahead then, and I'm going to do the do that whole substitution thing again. Okay, we have strontium here, 2 plus. Sulfate then is going to be a X2 minus. Okay, if we notice here then, 1 strontium, 1 X, okay, will give us a net charge of 0, and so therefore the formula then is going to be SR1 strontium. Remember, we don't have to write the subscript here if it's only 1, and 1X. Substituting in strontium back in for the X, we have then strontium, the sulfate back in here for X. We have SrSO4 as the formula for strontium sulfate. Okay. All right. Let's go ahead then, and I want you, let's go ahead and let's work this out. I would like you to go ahead, and if you can, if you feel comfortable at this time, you guys, skipping the step here that I've highlighted in red, please do so. Okay, so remember, at some point, and hopefully if you feel comfortable doing it now, you can skip this everything that I've highlighted in red here. You can skip all of that. If you can do that, fantastic. Please make sure you do that. Okay, so what I'd like you to do for number 3 and number 4, okay, I would like you to write out the formula for lithium carbonate, okay, and magnesium hydroxide. And this will finish out number 16 in your problem sub first. Okay, so again, for these two here, if you can skip having to do everything in red, please do so. If you can get straight to the formula, that's fantastic. But what I will do though is I will do everything in the red box, okay? And that way so that I'll help you. Okay, so take about 2 minutes if you need it, and then get the name, get the formulas for these compounds here, and then when you get back, we'll go over. Okay, so go ahead and get that done. Okay, let's go ahead and let's take a look at this. Okay, so hopefully you recognize then that both of these here are non-binary compounds, because both of these here have the polyatomic anions. Okay. All right, so then we can go ahead then and identify the metal in this one. The cation in this one is going to be lithium. The lithium cation, okay, is Li plus. The carbonate anion is Cr3, CO3 2 minus. Okay. All right, so with that said, then let's go ahead and do the quick substitution. Lithium then and carbonate being represented by an X with the 2 minus. Okay. All right. So in order to get to a 0-sum charge here, we need 2 of the lithiums for every 1 of the X's here. Okay. So we have then writing out the formula with that. It's going to be Li2 and 1X. Okay. Substituting back in carbonate for that X, we have then Li2 CO3. That is the formula for lithium carbonate. Okay. All right. Let's go ahead and let's take a look at then the last one, hydroxide here. Let's go ahead, and the cation is going to be magnesium. Magnesium is going to be a 2A metal, it's Mg2 plus. Hydroxide, hopefully you have that remembered, is OH minus. Okay, let's go ahead then and do again the substitution. We have then Mg2 plus for every X1 minus. Okay, and so if you notice here, To get to a net charge 0, we need 2 of the X's for every 1 of the magnesium. So therefore, the formula then is going to be Mg. It's going to be Mgx, and we need 2 of those right there. Okay, so that's what we need. So let's substitute back in the hydroxide. And so therefore, it's going to be Mg. X is going to be OH now. And we have to put parentheses around it because we need 2 of those in order to balance out the charges. So that is the formula for magnesium hydroxide. And if you notice again, just like with the binary ionic compounds, none of these formulas here have the charges in them. Okay? All right. Practice that, please, folks. Please make sure you practice that. That was the homework from section 9.2. I think that's a set B from chapter 9 that I assigned for you last week. Please make sure you come by and get your questions answered if you have any. Let's go ahead then, and what I would like to do is let's go ahead and let's get started with, and let me go ahead and save this here. Let me get started with the material from, let's go back to chapter 7, and let's take a look at what we have there. Please let me go ahead and put out of that. Let me get out of this one as well. Let me open up my next set of slides here. Okay. All right, so now that we have learned about ionic compounds and we've learned how to describe them, we've talked about how we name them, we talked about how we can write out their formulas. Okay, what we want to do then is I'm going to go back then and hopefully, if you have your Fit Lab available, we don't have the time for me to go over that Fit Lab with you, but come. If you have questions about your Fit Lab, please stick around. Come by today after school. I'll be available at 1:35 after my 7th period class. Come by and ask about that Fit Lab. Okay. But what we're going to do then is I'm going to go ahead and quickly just to share with you some of the properties of ionic compounds. These are what we can observe. These are the macroscopic properties of ionic compounds. What we have been doing is we have been basically describing what's going on at the microscopic level. How are the atoms interacting with one another? That's the ionic bond that we've been talking about. How we represent these particles on the microscopic level. We figured out then how many of each one of those atoms have to get together to bond together to make the ionic compound, the formula unit that we've been talking about. So those are all, the naming and the writing the formula. That's basically describing the ionic compound on the microscopic level, on the atomic level. Okay, on the macroscopic level, folks, we don't see those atoms. We don't see the bonding, but what we do notice are these properties here. First and foremost, that the ionic compounds tend to be crystalline in nature. You just take a look at the sodium chloride, for example. Okay, you take a look at sodium chloride. It is if you get a big enough crystal, you're going to see that it is a really nice looking crystal that you can break and then you can get smaller pieces. Okay? And many of the ionic compounds really have fantastic and colorful and beautiful crystalline structures. Okay, just Google it and you'll be able to see it. Okay, but most of them will be crystalline, crystal in nature at room temperature. Okay, so at room temperature, you're going to notice then that with most ionic solids, okay, most ionic compounds, they will be solids at room temperature. I actually cannot think of any ionic compound off the top of my head that is not ionic at room temperature. That is not a solid at room temperature. All the ionic compounds are solids at room temperature, and they will be crystalline in nature for the most part. Okay. All right. And the reason for this then is because ionic compounds will have a very high melting point, and I'm hoping that you were able to pick up on that in the Fit Lab that we did. Okay. So the reason why all ionic compounds are solids, crystal solids at room temperature is because they all have very high melting points. It takes a lot of heat to melt the crystalline solids, okay, to melt the ionic compounds. Look at ice. Ice is also a crystalline solid. Okay, but ice is not an ionic compound. It is a molecular compound, and we'll talk about that in chapter 8. But with ionic compounds, if you try to melt it, you're going to have to use a lot of heat to melt it. And so if you melt sugar, for example, table sugar is a crystalline solid. And you compare that to sodium chloride. You look at it, they look really similar to one another. Obviously, when you taste it, that's one difference. But when you melt it, you're going to see then that sugar melts at a much lower temperature than the sodium chloride, the table salt. Because and that should be, and that's one of the labs that we do in class, is that you're able to make that observations and use that to determine then that the two, the table sugar and table salt, are not the same because they have different melting temperatures. And obviously they're not the same because you taste it. But that's another key feature of ionic compounds that we can make use of to differentiate them from molecular solids. Okay? And we'll talk about molecular solids in chapter 8. Okay. Furthermore, then with ionic compounds, in when you add them to water, they always dissolve. Now, the process of dissolving and melting are two very different things. Make sure then that you do not confuse these here. Okay, melting requires heat. Melting requires heat. Okay, dissolving does not require heat. Now, folks always get these two terms confused, and I'm not quite sure why. But when you dissolve sugar, or when you dissolve sodium chloride in water, okay, you could add heat if you want to, okay, but you don't have to. You can add sodium chloride to water and it dissolves. And what do you notice when it dissolves? It looks like the solid disappears, but it doesn't disappear. This is not magic, folks. This is science. We'll talk about that in chapter 16. Why? What happens to the sodium chloride when it is dissolved? Okay? When you melt the sodium chloride, it becomes a liquid. It becomes liquid. So melting then is, both of these are physical changes. So let's make sure you keep that in mind. Both of these are physical changes. They're both physical changes because we are not changing the compound. We're not changing the compound that we're starting with. And both of these are reversible physical changes. And I'm sorry, let me put this in here. Both of these then are reversible. Whoops, sorry, let me remember. So both of these are reversible physical changes. Okay, but the key difference here: one requires heat, process of melting, and the other one does not require heat. Okay, so you got to make sure you keep that in mind, because that is a difference that is not subtle. It's not a subtle difference, and so hopefully you don't make this mistake. But it is a key difference. These two are very different processes, so please make sure you keep that in mind. Okay? All right, so with that said, then let me go ahead and clear this up. Let's continue to talk about these physical properties of ionic compounds. Okay? We know then that with ionic compounds, like I said, most of them are crystalline, not all of them. Sodium bicarbonate is an example of a solid that is sodium ionic compound that is a powder at room temperature. Okay. But with the ones that are crystalline solid in nature, okay, there is this repeating pattern of the ions that really make it fascinating. Okay? It's important here in understanding the properties of these ionic compounds. It's important to understand then this aspect here, that we have this repeating pattern of positives and negatives. Remember, we talked about that. We have this repeating pattern in which the in that particular arrangement, then you have a positive arranged next to a negative. Okay. The reason for that then is that we can minimize the repulsion between like charges, okay, and maximize the attraction between opposite charges. Okay. So that repeating pattern then will always be one in which you have positive followed by negative out in 3 dimensions. Okay? And again, the reason why we do that, the reason why nature does that, not we, we don't make it that way. The reason why nature does that is to minimize repulsion and to maximize the attraction of the ions. And it's for that reason that the melting point of ionic compounds are so high. Okay, so all right, so let me go ahead and let's continue on here. Okay. All right. So the large attractive forces between the ions, remember, these are electrostatic forces. This is a positive followed by a negative. So these large attractive forces here, these are the electrostatic interactions. So let me go ahead and highlight that for you. So these are the electrostatic interactions, which is what we talked about. Okay, the electrostatic interactions then are represented by the, so these are the electrostatic interactions. Okay, these electrostatic interactions, remember, is basically just the positive attracted to the negative. That is what we refer to as the ionic bond. It is large, it is huge, it is a very strong attraction. Okay, and so because of that, then that strength of that attraction requires a lot of heat to break it apart. Furthermore, what even makes it stronger, what makes it stronger is that the arrangement again of the positive and negative, the alternating positive and negative, not only in one dimension, okay, not only in two dimensions, but in three dimensions here, that makes that bond even stronger. So if two ions together, sorry, hold on a second. If two ions together have a very strong bond, if that electrostatic interaction is strong between two ions, imagine what that strength of that interaction would be between billions upon billions of ions in which you have this alternating charge here. And that's why this arrangement here, repeating arrangement of positive and negative, is so important for the strength of the bond itself, okay, the strength of the ionic compound itself. And so that is the reason why we see that it's going to take a lot of energy. It takes a whole lot of energy to disrupt this pattern here. It takes a lot of energy to go in and break up this interaction here. And again, this is just one small section. You can imagine this, but if you imagine this over three dimensions, over a large amount of space, it's going to take a whole lot of energy, okay, to disrupt that. Okay, so if the interaction between two ions is strong, okay, the interaction between millions upon billions upon billions upon trillions of those ions arranged with their opposite charges together will be even stronger. And so that is how we can explain that and account for then the strength of the high melting point of these ionic compounds. Okay. All right, so well, you know, that's okay. You know, we didn't quite get as far as I wanted us to get, and so you know, what we'll do then is I'll finish up this lesson on Monday. We'll review on Tuesday, and then the exam will be next Thursday. Okay, so but I do want to go ahead and start chapter 8 then on Wednesday. So next Wednesday we're going to start chapter 8, and the video on Wednesday will be about chapter 8. Okay, all right, very good, folks. Have a good weekend. Please come by and see me after school today if you have any questions. But please get your questions answered. Okay. All right. I will see you on Monday. Have a good weekend, folks.